So, good afternoon, everyone. I'll be talking about controlling the pulse width by the sample second-order dispersion to study instantaneous and non-instantaneous nonlinear refractions. So, what's our motivation? We know nowadays ultra-short laser pulses play important roles in fundamental and applied science because of their properties, like high peak power, short duration, and broad bandwidth. They allow nonlinear optical studies, which are important to characterize materials and develop new technologies, like photonic devices, or for instance, our optical switch. One key parameter in the material nonlinear effect is the material nonlinear effect index, N2, which can depend on the wavelength, on the laser pulse width, polarization, etc., presented in different components. To measure N2, it's important to know the pulse parameters, especially its temporal width and the linear shear. So we often need different measurement techniques to characterize the pulse or the sample. So here we propose to use our technique, nonlinear ellipse rotation, or NIR, that is capable to either obtain the samples N2 if you know the pulse parameters, or obtain the pulse parameters if you know the samples N2. Now we pretend to extend our technique to obtain N2 as a function of the pulse temporal width by using highly second-order dispersive samples. So let's contextualize our technique. In nonlinear optics, it's possible to define N2 by the Kerr effect originated by the third-order electric susceptibility tensor, chi3. In isotopic media, chi3 can be simplified as only two coefficients, A and B, and these coefficients can be related by its dominant mechanism that originates N2. So if non-resonant electronic effects are dominant, we have B equals A. If we have a molecular orientation dominant, B equals 6 times A, and for thermal effects, B equals 0. So NIR is a Kerr-type effect that appears when elliptically polarized laser beam propagates through nonlinear media. So if you scan the sample around the focal region, the rise in the intensity gives rise to a nonlinear effect in which there's a rotation in the elliptical polarization of the beam. The measurement is then related on determining this angle, which is related to B. To do so, we use a rotating polarizer, which modulates our signal according to Moyles' law, originating a cosine squared function. The rotation of the ellipse can be interpreted as a phase shift in the signal caused by the nonlinear effect, which can be measured by using a dual phase locking amplifier. A few years ago, our group proposed an experimental setup for the technique, which is very similar to the traditional Z-scan, differing only in the presence of a quarter wave plate and a rotation polarizer. The equation that describes the relation between the rotation angle alpha and N2 have a dependence on sine of phi, which is the quarter wave plate orientation, and on B, which determines N2. What's interesting about this equation is this final part that gives us our focalization regime. From the graph, we can see that, for thicker samples, we tend to form a plateau on the signal. This regime is also known as strong focalization, in which we use fixed samples in comparison to the lens short focal length. So this focalization regime allows NIR to be less dependent on the sample optical quality and on the beam mode, because one can perform self-reference measurements by scanning multiple samples at once. Also, the technique is blind to thermal effects, since B equals 0. So you can evaluate N2 in units of the signal, for instance, using it as a reference. But what about we using thicker samples? Notice that the NIR signal is proportional to the intensity and thus inversely proportional to the pulse width. That means that for thicker samples, we must take into account the group velocity dispersion that we call V2. Because our pulse have a broad bandwidth, so as propagation through media, it accumulates chromatic dispersion. Besides that, we must take into account the D2, that is the GDB, group delay dispersion, translated by the linear shear that will vary as the pulse propagates also through the sample. We then adjust NIR equation to take into account these effects as a function of the propagation L, the sample thickness, where tau 0 is going to be the transform limited pulse that has zero shear, and thus is the shortest pulse possible, which can be measured by spectrometer. So we also did that, and by using materials with well-known N2, we verified the different impulse shapes resulted in different linear signals, which were used to determine tau and D2, with it, including the 2 with its sign and also its absolute value. This technique also has its limitations. For example, this signal is based on high tree, so you need higher intensities, and also you need samples with high GVG, or else you're gonna have difficulties to fit the curves. But here we are interested in the case of using samples with non-instantaneous N2. So what about we use a sample of reference to determine the pulse parameters, but also our sample also has non-instantaneous nonlinear refraction. So we already knew from the past that performing measurements in different pulse widths, we could find N2 as a function of tau, thanks to the different response times of electronic effects and molecular orientation ones. So the Kerr effect could be written as a term N2 fast and a second term N2 slow, besides tau c that is a characteristic time. So we can use this behavior to prepare our next model. The idea here is that you need various measurements, and we are searching for, in a single measurement, determine N2 of tau. So is it possible to obtain N2 of tau with a single measurement? These are equations that we have so far. We can isolate B of tau and Z in this equation of NERS, and we can use the different parameters that we obtain from the pulse for all other measurements to plug in B and find how each relates to tau. So the experimental setup is similar to the already shown in this presentation, with the difference of the use of a spectrometer to calculate the bandwidth of the pulse, and the use of thicker samples, like in the order of centimeters. We operate a light conversion carbide laser of femtosecond pulses at 2 different wavelengths, 1030 nanometers and 515 nanometers. The pulse temporal width can be arbitrarily chosen by a pulse compressor, resulting in values from 216 femtoseconds up to 28 picoseconds. For the second harmonic, these values tend to be lower, approximately square root of 2 lower, so we need to take this into account also. So to determine the pulse parameters, we must choose a material with high GVG and without non-instantaneous N2. So we use the Selmayr equation of different glasses and convert these values to GVG. The best material that we found is SF6. It is a Scotch dense flint optical glass of calibration. We see that for the lambdas that we are interested, it presents the higher GVG values. So we also did this to our sample that will be used to calculate N2 as a function of tau. We chose CS2, carbon sulfide, which is a solvent. It also presents high GVG values at our lambdas, and due to its geometry, it presents high instantaneous and non-instantaneous nonlinear refraction, well studied in the literature. So finally, the results. First, we obtain the pulse bandwidth for both lambdas by spectrometers and convert to tau zero, resulting in 216 femtoseconds for infrared and 152 femtoseconds for green region. So that's the equation we use. We assume the pulse has a Gaussian distribution to facilitate our calculus. Then we measure SF6 glass at 1030 nanometers to determine tau and D2. Each measure have an indication of a plus value of femtoseconds or negative value of minus value of femtoseconds, representing each of the pulse widths that carbide laser generates, not including yet the broadening or the wide narrowing that the pulse will acquire through propagation. So the red arrows and the blue arrows represent measures which will induce more and more negative chirp or more and more positive chirp. So, as you can see, the NER fittings are adjusted and can be trusted. But you may be wondering, why do we need such fixed samples? Well, even though we are inducing more and more chirp, the signals doesn't seem to change that much. So it's harder to reach an accurate fitting. We thus find the 2 and tau at the entries of the sample for each pulse capacitor position, and then we can see that tau reach around 40 picoseconds due to the chirp gained as the pulse propagates through our experimental setup. We also performed intensity autocorrelation measurements using a Gecko setup, so we can compare our results for tau. We can see that the values are close, but in the NER setup, light propagates through more optical elements, and thus tends to be wider. The red dots are the expected pulse widths generated by carbide in its entrance shutter. So we also measure CS2 and obtain the NER signals that are represented by the black dots. The red lines is the calculated B of tau for each measurement, and it's possible for us to observe the behavior of positive and negative chirps, distorting our NER curve for increasing or decreasing values. So we will take each of these red curves that represent B of tau and plot them versus the pulse width as the beam propagates through the sample. So that's our result. You see the nonlinearity B value as a function of propagation versus the pulse width also as a function of propagation. We use the fitting proposed by our latest work. We can see that we achieve values of B fast, B slow, and characteristic time. We achieve these results for B effective. And comparing to the literature, we see that we have consistent values. So we can also convert B effective to N2 effective, and if we, for example, plug to 216 femtoseconds in this equation, we found a value of approximately 6.2 times 10 to the minus 19 meters squared per watt. That is pretty good. So that are the NER fittings using the B that we just found. And we can see that the results are pretty consistent, and we can prove that our model can interpret all the parameters involved in this system. So now we use the second harmonic of carbide. We follow the same procedure. First we use SF6 to find the pulse parameters. This time we can see that greater values of GVG cause greater distortions in the NER signal. The values are plotted as GDD and tau. We see that this time tau reaches up to 3 picoseconds. Again, we compare with Gecko. We find consistent results, but this time they are less well behaved, which can be attributed to the greater uncertainties, since the carbide second harmonic can't preserve the power. So as you switch to the second harmonic, we're losing energy, and you have to perform measurements of the power, peak power, average power in each measurement. So again, we take each curve of the NER signal and the B of tau curve, and we will plot this as a function of the pulse width as it propagates. So we do the same fitting, we found these values, we plug it, for example, 152 femtoseconds in the equation. We found N2 in the order of 7 times 10 to the minus 19, which is a little greater than what we found to 1030 nanometers, which is expected since CS2 have greater values as the wavelength decreases. So these are all the curves again. We see that some curves do not adjust very well, and this can be improved and will be improved in new measurements. So after all, already knowing the pulse parameters, can we determine N2 of tau with a single measurement? In these graphs, we can see the fundamental beam and the second harmonic. We see each color represents a single measurement. So we see, for example, that for higher DVDs, for example this, it seems easier to obtain B over a broad tau range. At 1000 nanometers, instead, each measure only scans a small portion of tau. So you perform a measurement and it scans only a small portion of tau. So you can, in a single measurement, guarantee that you are achieving an accurate fitting for your curve. But for the second harmonic, we see some measurements are closing to achieve what you want. You see that a single measurement can scan a broad range of tau. So in conclusion, maybe for now, it's safe to assume that few measurements are enough. But maybe in the future, we will have an alternative to perform these measurements without a pulse compressor, considering it's not a really usual thing to have in a laboratory. So anyway, now our single beam technique can also characterize ultra-short pulses by using materials with instantaneous and non-instantaneous N2, giving not only tau and D2, but also the sign of D2. As future perspectives, we hope to perform new measurements and improve our results, besides searching for materials with higher GPGs for better characterization. We pretend to characterize other solvents and test how much can we achieve for a precise N2 and tau using fewer measurements. So here are the reference. Thank you all, especially SPY, for the opportunity. Here is our group, located in São Carlos, Brazil. A huge thanks to Professor Lino Mizoguchi and Professor Emerson. Also, please visit our website. If you Google Photonics group, you can find it, and you can keep track of our publications. Thank you.